Bismillahirrahmanirrahim. Assalamu alaikum. This is Noor, your physics teacher, and today we're going to discuss the latest paper from the session February-March 2026, paper 4 of physics. Let's read the questions and also discuss the marking scheme. So, students, we have question number 1 here. Let's read it together. A student cycles from home to school. Figure 1.1 shows the distance time graph for this journey. So basically, a student cycling from home to school, the journey is being represented through the graph, which is showing to us on y-axis distance in kilometers, on x-axis time in minutes. The part A is asking, state the distance between home and school. How do we, state the distance? How do we work with the distance, the total distance from home to school? Simple. Look at the graph. And that too, look at the axis that is representing distance. Here, y-axis is representing distance. Fair enough. Starting from 0, see till where the graph traveled. Till wherever the graph traveled is basically the total distance that the student is actually covering. So how do we really work with it? We're simply going to say that we have this knowledge where 10 boxes are giving a value of 0.5. So therefore, one box, whatever value, we can simply figure it out through simple math here. We can say one box is going to give us a value of 0.05. And this is what we needed as well. So this is going to make it easier for us. If this is 1.5, after 2 boxes, it's going to be 1.6, and the value that we needed is going to be 1.7. So without any doubt, we're going to say the total distance from home to school that was traveled is 1.7 kilometers. Moving on. Now, when we talk about the next part is asking from us to state one point out of A, B, C, D, or E. We can see A, B, C, D, E points already marked on the graph drawing. So the question is asking, state one point out of A, B, C, D, or E, which identifies a time when the student accelerates. So how exactly are we going to work with this? We're simply going to look at the graph. The graph is distance time graph. And as per we know, a distance time graph's slope gradient is always going to give us the value of, to the speed. Yes, to the speed. So here we have the graph, distance time graph. So the slope, the gradient, the slope is going to be giving us the value to the speed. And if we can see from A till B, B till C, C till D, D till E, the slope is changing. We have been asked to tell where exactly, at which point exactly the student is going to accelerate. So we're going to see that point where the student's speed is going to start increasing. In other words, we're going to see through the graph at what exact point the student's speed, therefore the graph's slope is going to increase. So greater the slope, greater the speed. This is something we're going to keep in our mind. So if we can see from A till B, there is a slope definitely. However, at B point, we can see the slope starts to increase. In other words, speed starts to increase. So where exactly the student starts to accelerate, we're going to say at point B, because that is where we can see the slope is doing what? Is increasing. Therefore, the speed is going to increase. Therefore, student is accelerating. Moving on, the next part demanded from us to identify a time where the student decelerates. We have to now tell exactly where the student is going to decelerate. So to do that, we have to do what? We have to look at the graph once again, and we have to see where the slope exactly is going to decrease. Because where the slope is going to decrease, speed is going to decrease, student is going to decelerate. So at point C, we can see that the slope starts to decrease. So this is going to be that point where we're going to say that the student is decelerating. So B and C are going to be the right answers. Moving on. Now we have the next part, C part, which says use figure 1.1 to calculate the student's maximum speed in kilometers per hour. All right. The question is asking from us to calculate students' maximum speed, but in kilometers per hour. Not to forget, distance is in kilometers, but the time is not in hours, it is in minutes. So we need to do some little conversion over here. Let's do it. So since the question is asking calculate the student's maximum speed, we have to do what? We have to look at the maximum slope. Maximum slope, because maximum slope is going to give maximum gradient, therefore maximum speed. So maximum slope is something we already worked with, B till C. This is where we see maximum slope, therefore maximum speed. Moving on. So now we have maximum speed over here, but how do we really work with the value? We simply can, use rise over run, or we can simply use gradients formula. Let's have one. We are going to use over here gradients formula. We're going to say gradient of a distance time graph is going to represent speed. So gradients formula y2 minus y1 divided by x2 minus x1. Okay, so we're simply going to see that the point B is having coordinates 5 and 0.4, meaning the graph at point B has traveled till 5 value and on y-axis has traveled a value of 0.4. And now when we talk about point C, we can see that the graph here is showing horizontally it has traveled a value of 7.5 and vertically it has traveled a value of 1.25. So using these coordinates, we're simply going to find the maximum gradient, therefore maximum speed. So let's just put in the values 1.25 minus 0.4 divided by x2 minus x1, 7.5 minus 5. So this is going to give us a value of 0.34 kilometers per minute. So till here, we are doing it fine. However, minutes was not something that the question demanded answer in. So we have to convert this minutes into hours. How do we do that? Simple. Please recall. We have, if for example, 1 hour is equals to 60 minutes, we're going to keep in mind here, we're moving from a smaller value to a bigger value. And whenever we do this, we divide with the difference. What exactly is the difference here? 60. Okay. So we can write it in this way as well. 0.34 divided by 1 over 60. Fair enough. So we can simplify it further. 0.34 into, bring 60 here, and the answer, final answer is going to be, let's calculate. It's going to be around 20.4 kilometers per hour. So moving to the next question here. We have question number 2 in front of us, and question number 2 says, figure 2.1 shows a ship made up of steel floating on the sea. So we can see there's a ship made up of steel, and we can also see that it is floating where? It is floating on the sea. Fair enough. So the first part, part A part 1, is asking state the equation that links density, mass, and volume. We have the simple equation, density is equals to mass over volume. Density is equals to mass per volume. Okay. Next up, the question demands from us to part 2, the density of steel is 79,000 kg per meter cube. The mass of a solid steel cube is 110 kg. Calculate the volume. We do not have volume. We have mass. We have density. Just use the formula. Density is equals to mass over volume, and we're going to simply say density is what? Density is 7900. Mass is 110 kg. Volume is yet to be found. So we're going to make volume the subject. And when we do so, what exactly is going to be the answer? Let's find it out. Okay, so volume is equals to 0.0139. So this is something that we're going to remember. Moving on. The third part is asking the density of sea water is 1030 kg per meter cube. Okay, this is the density of sea water, 1030 kg per meter cube. State why the solid steel cube sinks when placed in seawater. So why exactly is going to be the solid cube sinking when placed in seawater? Because obviously we can see there's a density difference, guys. The density of steel was this much, and this exactly now is the density of seawater. Because of the density difference, density of steel is more than the density of water. So because of this difference, the steel cube is going to sink when placed in the seawater. So we're going to simply write over here, density of steel is greater than density of seawater. Moving on. Let's read the next part. Part 4 says, explain why steel ship in figure 2.1 floats on the seawater. Okay. In the previous part, we're telling that the steel cube is going to sink. And now we've been asked to explain why steel ship is not going to sink, rather it's going to float on seawater. We're going to understand that this is because steel ship is big enough. It is big enough, therefore air definitely is going to be trapped inside of it, is going to act through it. So when this situation is going to be there, we need to understand the overall density of the steel ship is going to decrease. So this is something that we're going to write here as well. Explain why steel ship in figure 2.1 floats on the seawater, does not sink, floats because of air. We're simply going to say, since steel ship is big enough, and further it has spaces in between, therefore air will be trapped inside of that ship. Moving on. So now we have the next part, part B. The mass of the ship is 3.5 into 10 raised to power 7 kg. The ship accelerates at 0.75 meter per second square. So we have mass, we have acceleration. The question asks, calculate the force which causes this acceleration. In other words, force find gradient. We have to calculate force, and there is a linking formula, mass into acceleration. So we do not have force's value, but since we have mass and acceleration, we're simply going to multiply the two, and we're going to find the force's value. Okay, so let's look into the answer. It's going to be 2.6 into 10 raised to power 7 newtons. Okay. So the next part is asking, explain why the force provided by the ship's engine must be larger than the value calculated in the previous part. Explain why the force provided by the ship's engine must be larger than the value calculated in the previous part. See, in the previous part, we calculated the value to the resultant force, net force, remaining force. We need not to forget that there are forces that are opposing the motion, that are acting opposite to the engine's force. For example, there is going to be water resistance, water drag as a force, resistive force. There's going to be air resistance. So engine must provide enough force to overcome the resistive forces, you see, and still leave a resultant force that we calculated in the previous part. So we're going to say what here? We're going to say that there are resistive forces such as water drag force, air resistance acting in opposite direction. So engine must provide enough force to overcome the resistive forces. Moving on. Now we have question number 3 in front of us. Question number 3 here says, figure 3.1 shows a polar bear and a person standing on thick ice. Okay. The figures are drawn to a scale of 1 centimeter ratio 100 centimeter. Okay. The table contains information, table 3.1 contains information about the polar bear and the person. We can see the diagram here. We can see the table here. And the part A is asking from us to calculate the weight of the polar bear. We can do that, right? Because the table is already giving us the mass of the polar bear. And we're simply going to do what over here? We're going to find weight, we're going to say W is equals to mg. And since mass is 590 and gravitational field strength is going to be taken as 9.81, the final value is going to be 5787.9. We can round it off to 3 significant figures and we can say 5790 newtons. Remember, if needed in the further calculations to the question, we're not going to use the rounded value. We're going to use this original value. Moving on. Next part says, calculate the pressure that the polar bear exerts on the ice. Pressure. So for pressure, one simple formula that we have is pressure is equals to force over area. Absolutely. So when we talk about force, here we've been asked to calculate the pressure that the polar bear exerts on the ice, force over area. We're simply going to say that force is equal to the weight that we calculated in the previous part. So we're going to take 5787.9 and the area that is in contact is going to be 1.12. So divide the two and the answer is going to be 5167.7. We can simply write 5170 pascals. Moving on. In the next part, we've been asked, use the numbers to complete each equation. Each number may be used once, more than once, or not at all. We're going to do one thing over here for our, ease. And that's going to be, we're going to take it as an equation where something is not known to us, and we can simply call it a simple variable. And this is how we're going to solve the equation. For example, mass of a polar bear is equals to dash into mass of a person. We have mass of a polar bear and also mass of a person already given to us in the table above. So mass of the polar bear, mass of the person is already something we are much aware of. So we're going to say what? Mass of polar bear 590, mass of person 84. Make it, work it as an equation. Mass of bear is equals to x into mass of person. This is something you do not know, so make it the subject. X is equals to mass of bear divided by mass of person. Mass of bear 590 divided by mass of person 84. What is the answer? Okay, the answer is going to be somewhat about 7. So this is something we're going to write. Okay, now moving to the next part, let's change the marker here. Now we have the next part, area of polar bear in contact with ice is equals to x into area of person. Okay, area of polar bear and person is something we are also aware of because this is area of polar bear and this is area of person 1.12, 0.02. Okay, so we can say area of polar bear 1.12 and area of person in contact with ice 0.02. Fair enough. So what exactly we're going to do over here? We're simply going to write area of bear is equals to x into area of person. We can make this the subject and we are going to be left with area of bear divided by area of person. What further? Area of bear is 1.12 and person 0.02. What is going to be the answer now? Yes, it's going to be 56. So we're simply going to write over here. Here we wrote 7. Here we're going to write 56. Let's look into the last one. So the last one says that the pressure exerted by the person is equals to x into, person is equals to x into pressure exerted by polar bear. So pressure exerted by person is something we're not aware of. Remember pressure exerted by polar bear we did find in the previous part, one of the previous parts, and this was it, the unrounded value. So 5167.7 is going to be the pressure exerted by polar bear. So let's just have it written in equation form as well. Pressure exerted by person is equals to x into pressure exerted by bear. Make x the subject. What are we going to be left with? Pressure of person divided by pressure of bear. We do not have pressure of person. We have pressure of bear. Let's write it as it is. What was it? 5167.7, I believe. So pressure of person, we can find, right? We can work with it. So to actually do that, what are we really going to see? We're going to see that to actually find pressure of person, we have a formula, pressure is equal to force over area. And once again, force is going to be weight, M into G, and area as it is. So mass is what of the person? Mass is 84 and gravity is going to be taken as 9.81. And we have area in contact 0.02. So what is going to be the answer here? It's going to be around 41202. So this is the pressure that is being exerted by the person. So we're simply going to write the value here and it's going to be what? It's going to be 41202. Divide the two and see what's the answer. What's the final answer? 7.9. Okay, so we're going to take it as 8. So here we're going to say 8. So 7, 56, and 8 are going to be the numbers that we're going to choose. Moving on to the next part. It says under the ice is seawater with a density of 1030 kg per meter cube. Okay, under the ice, is seawater with the density. So we've been given the density of sea, which is 1030 kg per meter cube. Absolutely. So the question says, calculate the change in pressure between the top of the seawater and at a depth of 2.5 meters. So basically, there's a height depth, which is 2.5 meters. Okay, so the values are already in SI units. We need not to perform any conversions here. However, how do we find the change in pressure? We're simply going to see that here we're talking about a liquid. And to actually work with liquid pressure, we have a formula which says rho GH, density into gravitational field strength into height. We have density already given to us in the question, 1030 kg per meter cube. We have gravitational field strength, which is 9.81, and a depth of 2.5 from the sea level. So let's see what's going to be the final answer. Multiply the three. All right, so we have final answer as 25,260.7, and we're going to write it as we can 253 with further two zeros pascals. So this is going to be it. Let's look into the next. Okay, we have a next question, question number 4 here. And it says an outdoor heater warms people sitting outside. Figure 4.1 shows the heater. Okay. So the heater, outdoor heater is given a labeling here. There are people around. Okay. Let's see what the question says. State the method of thermal energy transfer that warms the people. State the method of thermal energy transfer that warms the people. So we already have three methods, conduction, convection, radiation. Which one works here? Not conduction, because obviously for conduction to be the method for the transfer of heat, we need to understand that the particles must be in contact with each other. Here, obviously, the people, heater, they're not in contact with each other. So the conduction is never going to be the right method. Conduction, big no. What about convection? When we talk about convection, it takes place in fluids, right? In fluids. And when we talk about, the situation here, definitely the heater must be surrounded with air particles that are going to do what? That are going to take the heat from the heater, absorb it, and accordingly warm up the surroundings. But then again, is convection going to be the right method? The answer is again, no. Why? Because in convection, the absorbed heat, the particles that are going to absorb heat are not going to sink. If you guys can see, the heater is at some height from the people sitting. So how exactly the people are going to, get the heat from the heater? Because in convection, when the particles are going to absorb heat, they're going to become lighter and they're going to rise. They're not going to sink. So in convection, we're going to say because the particles are going to rise and the people, they're not above the heater, they're below the heater. So convection, once again, is not going to be the right method as well. So we're going to say radiations. So radiation is going to be the right answer. So radiation is the method through which the heat energy, thermal energy, is going to transfer from the heater and warm up the people. Moving on to the B part. B part 1 says, complete the sentences about energy transfer that warm the table. Energy transfer. We need to understand that we're talking about the transfer of energy. Let's see. Let's read it together. Let's be together. Be with me. Okay. It says that the heater transfers energy to the dash store of table. A little odd, but then again, if heater is transferring energy to a certain store, to the table, we're simply going to understand it's going to be the thermal store. So we're going to write over here, it transfers energy to the thermal store of the table. Fair enough. The temperature of the table increases, the rate of energy dashed by the table, absorbed by the table, is greater than the rate of energy dashed by emitted by the table. Moving on. One of the people puts a white cloth over the table. Explain why white cloth causes temperature of the table to decrease. Explain why white cloth. We already know that white, shiny surfaces are poor absorbers of heat. And they are good reflectors. They are good reflectors of heat. So we're simply going to give this same description over here. We're going to say that white surfaces are poor absorbers of heat. They're good emitters, heat. Not good emitters here, sorry. We're going to say they're good reflectors. So white cloth will absorb less heat. Moving on. So now we have the next part, which says the heater has a power of 2.5 kilowatts. Please do not miss this. Kilowatt. The heater is switched on for 3 hours. Calculate the energy in kilowatt hour transferred electrically by the heater. Okay, so we're going to understand that we have power, we have time, and we've been asked to calculate energy. Is there a formula that links the two? The three? The answer is yes. The simple one, power is equals to rate of energy transfer, energy over time. So this is going to be something we'll work with. So we have power, we have time, and the unit conversion is not required because the answer is not really changing the unit here. So we're going to simply work with the same units. So power is what? 2.5 kilowatts. Fair enough. And time is 3 hours. So we are going to do what? We're simply going to multiply the two, and energy is going to be calculated. So what's the answer? Yes, 7.5 kilowatt hour is going to be the final answer. Moving on to the question number 5. We have question number 5 here in front of us. Let's read it out as well. Question number 5 says atmospheric pressure is 1 into 10 raised to power 5 pascals. Okay, this is the atmospheric pressure that we have, 1 into 10 raised to power 5 pascals. A volume of 1.02 meter cube of air at atmospheric pressure. Okay, this is the volume of air at atmospheric pressure. Okay. So it is further saying is pumped into a car tire. The pressure of the air is the pressure of air when it is inside the tire is 2.6 into 10 raised to power 5 pascals. So in other words, we can see that the pressure is changing. Outside, the atmospheric pressure was 1 into 10 raised to power 5, and inside it is 2.6 into 10 raised to power 5. So it is definitely showing a change. What exactly the question is asking? Calculate the volume of air when it is pumped inside of the car's tire. Okay, so we are asked to find the volume. Okay, so we have the initial pressure, initial volume. We have the final pressure, but we do not have the final volume. We are simply going to use the formula P1 V1 is equals to P2 V2. Fair enough. We have pressure initially, volume initially, and we have final pressure, but not the final volume. So we're going to make final volume the subject, P1 V1 divided by P2. So we're just simply going to add in the values here. The values are 1.0 into 10 raised to power 5 into 1.02. Divide it with the final pressure, which is 2.6 into 10 raised to power 5. What is the answer? The answer is 0.392. So this is something that we're going to tell here. Moving on to the next part. Part B says, part B1 says, describe the structure of a gas in terms of the separation, arrangement, and motion of particles. Separation, arrangement, motion of particles. Please do not really confuse yourself. This is a separate part, which is asking from you the general properties of gas particles. So we're going to talk in terms of separation, arrangement, motion of gas particles. We're simply going to recall the general basic properties of gas particles. For example, when we talk about separation, we need to understand that they're far apart from each other. They are widely separated. They're far widely separated from each other. Okay, arrangement. How are they arranged? Randomly, random arrangement. All right, moving on to the next part. It says motion. We have to talk about motion as well. We need to understand that they're constantly moving and they're moving in random directions. So we're simply going to add here random motion and constantly moving. Moving on. Next part says, explain in terms of the particles why the internal energy of the gas decreases when the gas is at lower temperature. Fair enough. So we've been asked to explain in terms of particles, why the internal energy of gas decreases when gas is at lower temperature. So we're going to understand whenever the gas is going to have less temperature, the gas particles are going to have less speed, less kinetic energy. So explain in terms of particles why the internal energy of the gas decreases when gas is at lower temperature, because the average kinetic energy of the gas decreases, causing them to move at slower rate. So we're simply going to write here the average kinetic energy of gas particles decreases. Therefore, the speed decreases, making them move slower. So next question number 6 is right in front of us. Let's read it out. Figure 6.1 is a full-scale drawing, meaning you can simply pick up the ruler and measure the values. They're going to be accurate. They're going to be correct. So figure 6.1 is a full-scale drawing of an object O. Okay. A thin converging lens L and the image I of the object. Identify Z. So this is Z that we have in front of us. Identify Z. What is Z? We have to identify. Always remember, wherever you see a lens diagram and a horizontal line passing through the optical center, we're always going to remember that the horizontal line, which is going to be passing through the optical center, is going to be known as principal axis. So this is going to be principal axis. Z is going to be principal axis. Moving on. It says in part 2, determine the focal length of the lens L. Show any working in the space provided or on figure 6.1. So determine the focal length of the lens L. Focal length, what exactly is focal length, guys? Focal length is the distance between optical center and the focal point. So we need to find the focal length, meaning we have to find the distance between optical center and the focal point. How do we do that? To do that, we need to have focal point, right? But we do not have focal point. All we have been provided with is object, lens, and image. We do not have a focal point. However, there is one way. Do you remember the principal ray? Principal ray is basically that ray which is going to travel parallel to the principal axis before hitting the converging lens. So we're going to use that ray which is going to be parallel to the principal axis till before it hits the converging lens. And as soon as it is going to hit the converging lens, it is going to pass through the focal point. Okay. So since we had images mark here, point here, we already know where exactly the principal ray, the ray that is moving parallel to the principal axis before hitting the converging lens, is moving. So we had that principal ray and we also had the images mark. We're going to draw a line which is going to cross at some certain point through the principal axis. So the point at which it is going to cross the principal axis is going to be known as the focal point. And since we were asked to determine the focal length, we are now simply going to see pick up the ruler and see whatever the distance between optical center and the focal point is, whatever the distance is going to be the focal length. Moving on. We have the next part, part 3. The image in the figure 6.1 is inverted. And this is what we see here. Look at the arrow. It is upside down. So therefore, it is representing that the image is inverted. Moving on, state 2 other characteristics of the image. Okay. So one, that the image is inverted is already given to us by the examiner. We have to state 2 more characteristics of this image. Okay. Since it is up to the scale, pick up the ruler, measure this height and this height. You're going to see that they have the same value. So the first characteristic that we can come up with is going to be that image is of same size as the object. Okay. Number 2, we can also say that here the light ray is actually hitting the lens and passing through the lens and meeting at some common point. So it is going to be an image which we can call as a real image, where the light rays are actually meeting at one common point to form an image. So we're going to say this is going to be a real image. Moving on to the next part. It says, part B says, figure 6.2 shows a different converging lens with a focal length f. Okay. With a focal length f, fair enough. We can see here and here, we can see the focal length f already marked. It says the lens in figure 6.2 is used as a magnifying glass. Fair enough. This works as a magnifying glass, guys. In other words, the image is going to be bigger in size as compared to the size of the object. Draw an X on figure 6.2 to show a position of an object which produces magnified image. Okay. So it is a fact, a law that we've already revised. We have in our notes as well, that whenever the image is going to be magnified, to actually have a magnified image, the object must be placed between optical center and the focal point. So anywhere between these two dots, we can simply put a mark X. We did that. So anywhere between focal point and optical center, if the object is placed, it's going to give us a magnified image. Moving on. Put a tick alongside the two statements which describe the position of the magnified image. On the opposite side of the lens, bilkul bhi nahi. Why? Because it is on the same side of the lens. This is a fact. It is on the same side of the lens. So it's not a tick, it's a cross. This makes the second option clear, clear to us. This is going to be a tick. Then the same distance from the lens, no, it's going to have, greater farther distance from the lens. And this makes the last point clear to us as well. So point number 2 and point number 5 are the correct ones. Moving on. Moving on to the next question, which is question number 7 here. Let's read it out, guys. Question number 7 says, question number 7 says, figure 7.1 shows two identical cells in series with a thermistor and a fixed resistor. We can see a thermistor and we can also see a fixed resistor. Symbols are something that we should be much aware of. Moving on. So the switch is closed. Fair enough. Circuit is complete. The reading on the voltmeter is 9 volts. Okay, this is going to be 9 volts. The reading on the ammeter is 4.6 milliampere. So when we talk about 4.6 milliampere, please do not forget this, milliampere. It's not ampere, it's milliampere. So we're going to understand it's going to be not 4.6 ampere, it's going to be 0.0046 ampere. So if needed in calculation, we're going to use this value. Moving on. It says determine the EMF, voltage, EMF of one cell. Okay. Give the unit, fair enough. We have to talk about one cell's EMF and also the unit. So unit is going to be volt, definitely. And what about the EMF of one cell, guys? It said in the question, there are two identical cells. And if you guys can see and understand, this voltmeter, we do not have a value to the voltage given alongside these cells. However, the voltmeter is connected to the overall circuit, guys. So what exactly is this referring to? That if 9 volt is being shown here on voltmeter, it is 9 volts that the two cells collectively are providing the circuit with. So together, they're providing 9 volts EMF. So since one was asked and they're identical, we're simply going to do what? We're going to divide 9 with 2. Whatever the answer is going to be the answer of EMF to one cell. I hope that we understood. Moving on to the next part. So in the next part, we've been in B part, it says complete the sentence to define electric current. Complete the sentence to define electric current. Fair enough. Electric current's definition, we already know. Let's just fill in the blanks. Electric current is the amount of charge passing a point per unit time. Moving on, C part. The resistance of the fixed resistor is 480. Why not just mark it here? Resistance of fixed resistor is 480 ohms. 480 ohms. Okay. 480 ohms. Fair enough. Calculate the resistance of the thermistor. Okay. The thermistor is this one and we do not know the resistance. We have to calculate it and we can do that, right? How? if you guys can see, the resistors are connected to each other in series combination. So it's a series combination of resistors that we see here. And the rules, the facts that we have with us, one of the rules is that the current, because it is series combination of resistor, is not going to change. It's going to be the same throughout. However, because obviously it's passing from one point to all the charges are passing through each resistor. Moving on, we need to understand that to actually find the resistance, we have a very simple method here. For series combination, we say effective resistance or total resistance is equals to resistance of each resistor. We can simply add, since we have two resistors here, we're going to add first and second resistance. Okay. So the point is this, we have, for example, we can name one of them as R1 and the other as R2. We can simply say that R2's value we already have. It is what? It is 480 ohms. But the point is this, we do not have this, but we also do not have the total resistance. But students, we can actually find it out. You remember the formula, Ohm's law, V is equals to IR. What did it say? V is equals to IR. And if we want to find the total resistance, we need to have the total voltage, we need to have the total current. We have it. We have the total voltage, it is 9. We have the total current, it is 0.0046. We do not have the total resistance, and we can make the subject divide 9 with 0.0046. What is going to be the answer? The answer of total resistance is going to be 1957 ohms. So we have 1957 total resistance value. We do not have this thermistor's resistance, so we're simply going to write it R1. And we're going to add another resistance that we are aware of, and that is fixed resistors resistance for 80 ohms. So take it on the other side, and 1957, when is going to be subtracted by 480, whatever the answer is going to be the answer to the resistance of the thermistor. So the answer is going to be 1477 ohms. I hope that we understood. Moving on to the next part. It says the thermistor is placed in a beaker of ice. Okay. Beaker of ice, beaker of ice. In other words, temperature is decreasing. The temperature of the thermistor decreases. State how this change in temperature affects the reading on the voltmeter and ammeter. Okay, one idea that we need to have over here is it's not going to affect the reading on the voltmeter. Because why? The thing that we discussed initially, voltmeter is not just connected to the thermistor. It is connected to the overall circuit. It is connected to the overall circuit. So it is still going to show a value of 9 volts. So we're going to say voltmeter is going to show no change. It's going to show no change. And to actually write it down, we can simply say that it is going to be unchanged. Voltmeter reading is going to be unchanged. Moving on. What about the ammeter's reading? Ammeter is going to show us the current's value. What is current? Rate of flow of charges. You see, if the temperature is decreasing, resistance must be increasing. And if resistance is increasing, obviously it is a series combination of resistors. All the charges are going to pass through each circuit. However, when resistance is going to be more, the time taken is going to be more. So the current is going to reduce. So we're going to say the ammeter reading is going to decrease. I hope we understood. Is going to decrease. Moving on to the 8th question. Now, when we look at the 8th question, it says a transformer steps down high voltage electricity. A transformer steps down high voltage electricity. The transformer has 6,200 turns on the primary These are number of turns on primary coil, and 43 turns, number of turns on secondary coil. The output voltage, yani the voltage given through the secondary coil is 230 volts. So this is going to be the voltage of secondary. So calculate the input primary's voltage, input voltage in step down transformer. So we have number of turns of primary and we have number of turns of secondary. We also have we also have voltage of secondary, but we do not have voltage of primary. And this is something that we have to calculate. So we're going to use the formula voltage of primary divided by voltage of secondary, number of turns on primary divided by number of turns on secondary. Since we do not have this is going to be what we're going to make, what we are going to be making the subject. So voltage primary is going to be number of turns primary divided by number of turns secondary into voltage secondary. Moving on. So we have here 6200 divided by 43 into, yes, 230. So the answer that we're getting over here is okay. So this is going to be the value that we are going to round up to 3 significant figures, and it's going to be around, okay. So this is something that we calculated as the primary's voltage, input voltage. Moving on to the next part. Next part says a 2.2 kilowatt kettle is connected to the secondary coil of the transformer. A 2.2 kilowatt kettle is connected to the secondary coil of the transformer. Okay. Basically, this is the power connected to the secondary coil of the transformer. It says calculate the current in the primary coil. Okay, we're simply going to write what we need to find here. Calculate the current in the primary coil of step-down transformer. Assume that the transformer is 100% efficient. This is going to make one thing clear to us, and it's going to be whatever the input power, it is going to be the output power. This is what 100% efficient means, stands for. So we're going to say the power input or primary is going to be power secondary. Okay. So we already had the secondary's power, and it was, for example, 2.2, but it was kilowatts. So this is not what we're going to write in calculation. We're going to simply use power 2,200 watts. We're going to remove the prefix. So the same power could be used if required to find anything. For example, find current in the input primary side. So we have input. So we have input power. We're simply going to write over here, primary side power is 2,200 watts. We also in the previous part figured out input voltage. So we're going to have input voltage here, but this is not going to be the final answer. It's not going to be the one that we're going to be using. We're going to be using the unrounded answer. Voltage of primary is equal to 33162.7 volts. So now we have power on the primary side and we have voltage on the primary side, but we do not have the current. Can we find it? Absolutely. We have a few formulas and there is one that links 3 very smoothly. We're simply going to write over here, power is equals to V into I. VI. So when we're going to do this, we're simply going to remember that we do not have current and we have to make current the subject. And when we're going to make current the subject, we're going to be left with power over voltage. So power was 2,200. Voltage was what? It was 33162.7. What's the answer that we're getting? It is 0.066 amperes. So this is going to be the current on the primary side of the coil. Okay, in the next part, it says, part B, a power station produces 1.3 gigawatt of electricity. Okay. A transformer at the power station steps up the voltage before electricity is transmitted. Fair enough. This reduces the power loss during transmission. State the equation for power loss in electricity transmission. You see, we have around 3 equations of power. For example, P is equals to V into I, the one we used right above. P is equals to V squared divided by R. P is equals to I square R. We're going to use P is equals to I square R. And remember, this is the equation which is used specifically for power losses. So in the next part, it says, explain how step-up transformer reduces power losses during electricity transmission. Explain how step-up transformer reduces power losses. We need to understand. And this is something you need to remember as well. Whenever we talk about step-up transformer, always remember, number one, step-up transformers does what? They increase the voltage. They increase the voltage. And this is something you are much aware of. They increase the voltage. And as they increase the voltage, the current decreases. Current is going to do what? It is going to decrease. And when the current is going to decrease, the power losses are going to decrease as well, as per the equation that we mentioned above as well. So this is something that you have to remember. Whenever we talk about step-up transformers, the voltage is going to be increased. However, the current is going to be decreased. Therefore, the power losses are going to be reduced. So this is something that you're going to keep in your mind. Moving on to the next question. So we have question number 9 in front of us. It says, figure 9.1 shows a beam of alpha particles, gamma radiations, entering an electric field between the two charged metal plates P and Q. P and Q. Okay. We can see two charged metal plates. P is having positive charge on it and Q is having negative charges on it. Moving on. A beam of alpha and alpha particles and gamma radiations are going to pass through it. Okay. In A part, it says on figure 9.1, draw the path of the alpha particles inside the electric field. Okay, alpha particle. We need to remember they're positively charged, right? And they're heavy as well. So these two properties are going to make us clear that since they're positively charged, they're going to deflect, move towards the negative plate. However, smoothly. Why? Because they are heavy. Number 2, the gamma radiation inside the electric field. Always remember, gamma radiations are not going to deflect due to magnetic or electric field because they're neutral. They're neutral. They're not going to show any deflection. They're going to pass straight through. And this is something we're going to call as gamma radiations. Okay, moving on. It says a student places a sheet. It says a student places a sheet of paper in the path of beam. Okay, before it reaches the electric field. State how this affects the path of alpha particles and gamma radiations inside the electric field. We need to understand that whenever we talk about alpha particles, they do not penetrate through, they cannot pass through paper, foil, this and that. We need to remember this. And they penetrate very less, barely a few centimeters. So we're going to understand if a paper is going to be placed in front of alpha particles, they're going to be stopped. They're going to be stopped. They're going to be stopped. Or they're not going to penetrate, they're not going to pass through. What about gamma radiations? They're going to be not affected. They will pass through. Moving on. So we have C part over here. It says the beam of alpha particles and gamma radiations in figure 9.1 is replaced by a beam of beta particles. Okay. Beta particles, negatively charged like electrons. Beta particles, they're lighter. Okay. State and explain the path of beta particles in the electric field. Use ideas about electrostatic force in your answer. Okay. What are we going to say over here? We're going to understand that beta particles are going to deflect sharply, quickly as compared to alpha particles, and also they're going to deflect towards the positive plate. So if we had to mark here, we would have marked it somewhat like this because they're lighter and they're negatively charged. They're going to be deflected towards positive plate, and that too sharply. So this is something that we're going to write here. Statement: beta particles will deflect more. Okay. And we're also going to add some explanation here. And the explanation is going to be because beta particles, they themselves are negatively charged. They're going to be deflected towards positive plate. And the answer is because unlike charges are going to attract each other. And the answer is going to be what? That the unlike charges are going to attract each other. So the positive is going to attract the negative beta. Okay, moving on. So we're going to write over here. Unlike charges attract. And we're also going to write over here, since beta particles are lighter, they will move quickly, sharply towards the positive plate. Moving on, guys. Now we have question number 10, and let's look into this question number 10 as well. Now, this question number 10 says a planetary nebula form as part of the life cycle of stars. Complete the sentence about the planetary nebula. Stars expand when they run out of hydrogen to fuel nuclear reactions. A dash forms a planetary nebula. We need to understand that this is that stage where the statement is saying that stars expand when they run out of hydrogen. So we're going to understand this is the stage where it is becoming a red giant star. Forms a planetary nebula. Number 2, state what is at the center of the planetary nebula. What is at the center? White dwarf. Okay. So these are the stages that we learned, and this is something that you need to revise as well. Okay, now it says a planetary nebula emits blue light and red light. Okay. A planetary nebula emits blue light and red light at two specific wavelengths, 5 into 10 raised to the power negative 7 meters and 6.6 into 6.6 into 10 raised to power negative 7 meters. Explain why the light with a wavelength of 5 into 10 raised to power negative 7 meter is blue light. It is simple. Whenever we talk about blue light, we need to understand that it is the light which lies in the blue region of the spectrum. It has shorter wavelength. So this is something we're going to write over here as well. It lies in the blue region. It is having a shorter wavelength. So this is something we're going to write here. Explain why the light with wavelength 5 into 10 raised to power negative 7 meter is blue light, lies in blue region of the spectrum. Has shorter wavelength. Moving on. The speed of light in vacuum is 3 into 10 raised to power 8 meter per second. Calculate the frequency of blue light. Okay. So the speed of light in vacuum is this. Calculate the frequency of blue light. The examiner in the previous part already gave us the wavelength of blue light, which was what? Which was 5 into 10 raised to power negative 7. So this is the information that we require because there's a formula which connects the three. V is equals to F lambda. We have to calculate frequency and we have we have the speed, which is 3 into 10 raised to power 8 meter per second. And we also have the wavelength of blue light, which is 5 into 10 raised to power negative 7. So let's just make F the subject here. We're going to be left with V over lambda. And we are going to put in the values 3 into 10 raised to power 8 divided by 5 into 10 raised to power negative 7. Whatever the answer is, the answer to the frequency 6 into 10 raised to power 14. So this is going to be it. We're going to write so this is going to be it. Moving on. So I believe now we have reached to the final question. Let's see. Let's read this out as well. So it says the average orbital speed v of an object in the solar system is defined by the equation. We already know the equation. Define the terms r and t in this equation. Okay. What is r? What is r? It is radius. It is the radius of the circular orbit. And now when we talk about t, what exactly is t? T Veto is basically the time period or orbital time taken for the completion. All right, so we're going to write here, it's going to be T is what? It is the time period. Moving on. So we have in the next part, the average orbital speed of Saturn is 9,600 meter per second. Okay, the average orbital speed is already given to us. Okay, 9,600 meter per second. Okay, so it says, explain why the orbital speed is an average value. The answer is very clear because in reality, planets have their elliptical orbital paths. It's not exact circular path. It is squashed circular path. It is elliptical path. So we're going to understand over here, explain why the orbital speed is an average value. We're going to understand because planets have their elliptical orbital paths. The radius is not same throughout. The distance from the sun is not same throughout. We take average radius, therefore average velocity. And we need to understand the velocity is changing. It is going to be greater when the planet is closer to the sun and the speed is going to be slower when the planet is farther from the sun. So what exactly we're going to explain over here? Explain why orbital speed is an average value. Because planets have their elliptical orbital paths. Radius is not constant. We take average radius, therefore average velocity. I hope we're good. Okay, the last part says Saturn is 1.4 into 10 raised to power 12 meters from the sun. Okay. Saturn is 1.4 into 10 raised to power 12 meters from the sun. Show that one Saturn year is approximately equal to 30 years. Fair enough. Fair enough. So we have what? We have Saturn's average velocity. We're going to simply write here, velocity is equals to 9600 meter per second. We have the distance from the sun. In other words, we have radius's value. This is radius's value, 1.4 into 10 raised to power, into 10 raised to power 12 meters. So what can we find through this given information? We can find the time period, the time taken for Saturn to complete one orbit. So time period. Okay. We can find time period. How so? We have the formula which said V is equals to 2 pi r divided by d. So we're simply going to make t the subject, and when we're going to do that, what are we going to be left with? T is equals to 2 pi r divided by v. Fill in the values. Let's see. 2 pi into radius, which is 1.4 into 10 raised to power 12. Divide it with the average velocity, which was 9600. Okay. So what exactly are we getting as the answer? Let me see. Okay, we are getting an answer of 9.2 into 10 raised to power 8 seconds. All right, we got the time period, the time taken for Saturn to complete its one orbit. But was this asked? The question said, show that one Saturn year is approximately equal to 30 Earth years. So we're going to keep it simple. Please look here. I'm just going to change the color of pen. Look here, guys. We're going to keep it simple. We're going to say if we have to compare with Earth year. So Earth, one Earth year is equals to 365 days. And since we have to talk in terms of seconds, we're going to say into 24 into 60 into 60. So the answer is going to be of the 1 year in seconds. Okay. So we're going to say that the answer that we're going to get is going to be 3.15 into 10 raised to power 7 seconds, guys. So in one Earth year, these many seconds are taken. Okay. So if Saturn's one orbit is taking 9.2, we can do some simple math here. I am short with space. I'm just going to use this space. Guys, please look here. So we're going to simply say that one Earth year is equals to 3.15 into 10 raised to power 7. Therefore, how many Earth years are going to give us a value of 9.2 into 10 raised to power 8? And when you're going to further simplify, use some simple math here. you're going to get an answer which is going to be approximately 29 something. So this is what the question demanded. Show that one Saturn year is approximately up to 30 Earth year. So this is it. I hope you understood. And we're going to be uploading a few more papers. Thank you so much. Allah Hafiz.